Students, in the last session we had discussed a lot on analytic functions. In this we will be discussing a little on transformations and more on complex integration. Transformation. Suppose w equal to fz is a function, then for every point p with coordinates xy in the z plane, there corresponds a point with coordinates u, v in the w plane. Suppose the transformation fz is equal to z square, then we know that u is equal to x square minus y square and v is equal to 2xy. Therefore, the point 1 in z plane will correspond to the point 02 in the w plane, and thus a curve on the z plane will correspond to another curve c dash in the w plane. Thus, a function w equal to fz defines a mapping or transformation from z plane to the w plane. Bilinear transformation. The transformation w equal to az plus b upon cz plus d, where a, b, c and d are complex constant, is called as the bilinear transformation. Again, the inverse transformation is also bilinear. For this given bilinear transformation, we can write exactly like this. So instead of these four constants, here three constants are enough. And one problem, find the bilinear transformation which maps the point 0, minus 1 I of the z plane onto the points 2, infinity, half, 5 plus I of the w plane. This is the bilinear transformation. We have to just determine values of these constants. First combination, z equal to 0 maps into w equal to 2. Putting in here, we are getting second constant as 2. On second combination, z equal to minus 1, w equal to infinity, we are getting the third constant as equal to 1. And using the remaining combination, we are getting the first constant as equal to 3, and hence the bilinear transformation is equal to w equal to 3z plus 2 upon z plus 1. We can always check, you can put values of z and you will find corresponding of the w. We can check our answer whether we are correct or not. Show that the map w equal to 2z upon plus 3 upon z minus 4 transform the circle x square plus y square minus 2 x equal to 0 into the straight line for u plus 3 equal to 0. So w equal to fz, this is the transformation. Let us put z is equal to x plus iy. After simplification, we are getting real part and imaginary part. Real part is u, which is equal to 2x plus 3 times x minus 4 plus 2y square and divided by x minus 4 whole square plus y square. This is u, and after simplification, for u plus 3 is equal to this. For u plus 3 equal to 0 implies that 11x square plus 11y square minus 44x equal to 0. That means x square plus y square minus 4x equal to 0. That means this and both the things are same under this transformation. Here you can try with these two problems on bilinear transformation and complex integration. Suppose this is an arc in the two-dimensional complex plane. Function fz is defined for every point in this arc C. Then integration along the arc C fz dz is equal to, this is the definition, fz equal to u plus iv, dz equal to dx plus I times dy, and that is equal to, real part is u dx minus v dy plus, again integration, imaginary part is going to be v dx plus u dy. Quickly, one problem based on this. Evaluate integration z conjugate square dz from origin to 2 plus I along the line x plus 2y. This is first problem, and second problem is the same integral is to be evaluated from origin to the real axis 2 and from 2 to the point 2 plus I. So let us simplify the integrand first. Z conjugate means x minus iy. After simplification, we are getting value of the integrand in terms of x and y like this. Now in the first integration, which is from 0 to b along the straight line x equal to 2y, so we'll be substituting x equal to 2y, therefore dx is equal to 2 times dy in this. So everything will be in terms of y. This is the expression, limits of y from 0 to 1. We are getting the answer 5 by 3 times 2 minus I. The same problem can be converted in terms of x only. You can make the substitution y equal to x by 2, dy will be equal to dx by 2, but the limits of x will be from 0 to 2, and we are going to get the same answer. The second half of this problem, so the same integrand is to be evaluated by another route from origin to this point and from this a to b. So again we will be dividing this into two parts. In the first part, the integral is from 0 to a. An equation of this is y equal to 0, so dy will be equal to 0. Put here, and after that limits of x changes from 0 to 2, and we are getting answer as 8 by 3. Then evaluating the integral from a to b, equation of this line a to b is equal to x equal to 2, and therefore dx will be equal to 0. Would simplify, and now the limits of y will be 0 to 1. We are getting the answer 2 plus I times 11 by 3. And the second integral from origin to point B along this path, that is coming as 14 by 3 plus I times 11 by 3. It is different than what we had got in the first part. The reason is obvious. Here fz is equal to z conjugate whole square is not an analytic function. Very important Cauchy's theorem. If fz is an analytic function within and on a closed curve C, then integration over closed curve C fz dz is equal to 0. And three corollaries are coming automatically from this. The line integral of an analytic function in a given region R is independent of the path joining any two points of the region R. So integration fz dz along C1 will be same as integration fz dz along C2. Corollary 2. If fz is an analytic in the region R between two simple closed curves C and C1, then integration fz dz over C is same as integration fz dz over C1. Corollary 3. If C1, C2 and so on are any number of closed curves within C, then integration fz over closed curve C is equal to integration fz dz over C1 plus integration fz dz over C2 and so on. Again we will be quickly solving this. I have explained this problem briefly. Verify Cauchy's theorem for the integral fz equal to z cube taken along the boundary of a rectangle with these 4 points. Now fz equal to z cube, that means f dash of z equal to 3 z square, which is finite for every finite z. So fz equal to z cube is an analytic function, and therefore by Cauchy's theorem we must show integration over closed curve C fz dz must be equal to 0. So here we have simplified fz dz, and that is in terms of x and y. Now we have to evaluate the integral along the boundary of the rectangle. So there are obviously 4 parts. In the first part, the point -1 to +1. For this, value of y is equal to 0 and dy will be equal to 0. Integrate from x equal to -1 to +1. We are getting answer is equal to 0. In the second part, we find from 1 to 1 plus I. So in this, x is equal to 1, dx will be equal to 0, and limit of y will be from 0 to 1, and that is coming as -5 by 4. In the third part, from 1 plus I to -1 plus I. Here y is equal to 1, dy equal to 0, and x is changing from -1 to +1. We are getting answer as 0. And finally, -1 plus I to -1. So here x is equal to -1 is fixed, therefore dx is equal to 0, and y is changing from 1 to 0. We are getting answer 5 by 4. Addition is equal to 0. That one has to get. Evaluate integration over closed curve C 1 upon z square dz, where C is a circle, modulus of z is equal to 1 means standard unit circle. So we see that fz equal to 1 upon z square. This is not analytic at the point z is equal to 0, which lies within on or this circle. So we cannot make use of Cauchy's theorem. We know that z equal to r e to the power I theta and modulus of z, that is r is equal to 1. So obviously z is equal to e to the power I theta, dz equal to e to the power I theta into I into d theta. So sitting here, we are getting value of the integral is 0. Now we realize that converse of Cauchy's theorem is not true. That means I want to say that value of this integral is 0, and if we see back, fz is not analytic. Actually, what Cauchy's theorem says that if fz is analytic within and on a closed Cauchy, then integration fz dz is equal to 0, and definitely the converse of any statement is never true, and here also the same thing is happening. Cauchy's integral formula. If fz is analytic within and on a closed Cauchy and a is any point within C, then fa equal to 1 upon 2 pi integration over closed Cauchy fz upon z minus z dz. Further, f dash of a equal to 1 factor upon 2 pi integration over closed Cauchy fz upon z minus z square dz, and so on. We can generalize this result. So this is a particular case of Cauchy's residue theorem, which we are going to learn soon. Every problem which is solvable by Cauchy's integral formula is also solvable by making use of Cauchy's residue theorem. Evaluate integration over closed Cauchy z square minus z plus 1 upon z minus 1 dz, where C is the circle. So first part is modulus of z is equal to 1. Now we have to decide what to take as fz, only numerator or the entire thing. Now z, absolute value of z is equal to 1 is a circle with center at origin and radius is equal to 1. We see that z is equal to 1 is lying within or on this, so fz will be considered as numerator only. Fz is analytic within and on closed Cauchy, and z is equal to 1 lies within on or the circle. Therefore, by Cauchy's integral formula, f of 1 equal to 1 upon 2 pi I integration over closed Cauchy fz upon z minus a dz, and therefore this is equal to 2 pi I into f of 1. F of 1 is 1 square minus 1 plus 1, that is 1, and the answer is 2 pi I. Another problem, the same integral but tau modulus of z is equal to half. This is a circle with center at origin and radius half. So this z is equal to half is the radius, and z is equal to 1 is lying outside the circle. So here we can take fz as the entire thing, z square minus z plus 1 upon z minus 1, and we realize that this is analytic within and on a circle, z is equal to half. So by Cauchy's theorem, integration over closed Cauchy fz dz is equal to 0. Quickly, next problem, integration over closed Cauchy e to the power 2z upon z minus 1 into z minus 2 dz using Cauchy's integral formula, where C is a circle with modulus of z equal to 3. This is a circle with center at origin and radius 3. So the integrand is simplified like this. We can write this as two different integrals like this, and let us concentrate on the first integral. Circle with center 0 and radius 3, z is equal to 2 lies within or on the circle, therefore fz equal to e to the power 2z only, and that is equal to 2 pi I into f of 2, where fz equal to e to the power 2z, so f of 2 will be e to the power 4, so 2 pi I into e to the power 4. And the second integral, here again fz equal to e to the power 2z is analytic, and z is equal to 1 lies within on or the closed Cauchy, so that is equal to 2 pi I into f of 1. F of 1 this time is e to the power 2 into 1, that is e to the power 2. So another easy problem. Integration over closed Cauchy e to the power z upon z plus 1 into z plus 2 dz, where C is the circle, z plus 1 modulus of z plus 1 is equal to half. So this is a circle with center x equal to minus 1, y equal to 0, and radius is equal to half, like this. this. So again we can simplify, we can take advantage of this. We realize that z is equal to -1 is lying inside, so we'll define fz as equal to e to the power z only. So integration over closed curve c fz upon z plus 1 dz is equal to 2 pi I into f of -1. F of -1 is equal to e to the power -1. For the second integral, e to the power z upon z plus 2. Now z is equal to -2 is lying outside, so we can consider fz as the entire thing. E to the power z upon z plus 2 is analytic within and on the closed curve C. So by Cauchy's theorem, integration for closed curve C to the power z upon z plus 2 dz is equal to 0. And adding, we are getting answer of this integral as this much. Another way to solve the same problem is here. E to the power z upon z plus 2 is analytic within and on closed curve C, and z is equal to -1 lies. So by Cauchy's integral formula, integration over closed curve C fz upon z plus 1 is equal to 2 pi I into f of -1. F of -1 is equal to e to the power -1 upon -1 plus 2. And we have to get the same answer. All these problems can also be solved by Cauchy's residue theorem. Again, just have a look on this. Evaluate integration closed curve C z plus 4 upon z square plus 2 z plus 5 dz, where C is the circle modulus of z plus 2I is equal to 3 by 2. We have to just simplify and get the factors of the denominator, and again you have to make use of the integral formula. Everything is clear. We have already solved some problem on this, and the same problem can be alternatively solved. You can press a pause button, can see till you are convinced, like this. So these are additional problems with answers. You can try on with these problems also. And the most important, Cauchy's residue theorem. If fz is an analytic function within or on a closed curve C except at a finite number of isolated singular points within C, then integration over closed curve C fz dz equal to 2 pi I times sum of residues at these singular points which lie within or on the closed curve C. Residue of fz at a simple pole z is equal to a given by z minus a times fz, and then put z is equal to a. Residue of fz as a multiple pole z is equal to a of multiplicity r is given by 1 upon r minus 1 factorial into r minus 1 the derivative with respect to z of z minus a to the power a r into fz, then put z is equal to a. Evaluate integration over closed curve C sin pi z square plus 2z upon z minus 1 square into z minus 2 dz, where C is the circle modulus of z is equal to 4. When we are going to try with Cauchy's residue theorem, absolutely no problem. You can treat only numerator, the entire thing as f side. So the integrand itself is f side, and it is analytic except at z is equal to 1 and z is equal to 2. So these are the 2 points of singularity. Z equal to 2 is simple, whereas z is equal to 1 is a double point. Residue at a simple pole z is equal to 2 is z minus 2 times fz, and then put z is equal to 2, we are getting it as 4. Residue at the double pole z is equal to 1 is 1 upon 1 factorial into first derivative of z minus 1 square into fz, this much, and then put z is equal to 1. Now we see numerator denominator both are functions of z, so we have to make use of quotient rule, and after using the quotient rule it is simplified as 2 pi minus 4. Now integration over closed curve C of z dz equal to 2 pi I times sum of residues at both the poles. So the addition of the residues of the poles is 2 pi, and that will be multiplied by 2 pi I, and the answer is equal to 4 pi square I. Evaluate using residue theorem integration over closed curve C 2z square plus 2z plus 1 upon z plus 1 cube into z minus 3 dz, where C is the counter z plus 1 is equal to 2. Now this is a circle with center at x equal to -1, y equal to 0 and radius is equal to 2. So you can draw that and you can judge whether these 2 points of singularity z is equal to -1 and z equal to 3 lie within the circle or not. Another way you can directly straight away put here and then guess whether this any point lies within or on this or not. Now z is equal to -1. If we are putting z is equal to -1, so that becomes modulus of 0 and that is less than or equal to 2. So obviously z equal to -1 is going to lie within or on this circle. What about z is equal to 3? Modulus of 3 plus 1, that is 4, that is exceeding 2, so it is lying outside. Even if we do not draw the diagram, still we can realize. So here we have to find residue at only one point. Z is equal to -1 and z is equal to -1 is a multiple pole of multiplicity 3. So residue of z 1 upon 2 factorial second derivative with respect to z of z plus 1 cube into fz and then put z is equal to -1. That is simplified and that is coming as -25/64 and integration over closed curve c fz dz is equal to 2 pi I times this quantity and that is coming as -25 upon 32 times pi I. This can be tried by yourself. Another way to find residue of fz is equal to phi z upon psi z at a simple both z is equal to a is find fz is equal to phi z upon derivative of phi dash of z at z is equal to a. This is useful specifically when the denominator is a trigonometric function. So here evaluate integration over closed curve c tan z dz where c is the circle modulus of z equal to 2. So so many poles are there, but amongst these poles only two poles lie within or on the circle modulus of z is equal to 2. So we have to find residue as both these points, and for both these points the residues are -1 each. 2 pi I times -2, that is -4 I pi I is the answer. You can try the next problem, and this is another variety. So we'll try to solve this. Evaluate integration over close of from 0 to 2 pi of 1 upon 5 plus 4 sin theta d theta using residue theorem. So here we consider a standard unit circle, that is modulus of z is equal to 1. Z is equal to e to the power I theta, so dz will be equal to e to the power I theta into I into d theta. Therefore d theta equal to dz upon Iz, and we know sin theta is equal to e to the power I theta minus e to the power minus I theta upon 2I. So in terms of z, so theta is going to, here theta is going to be expressed in terms of z. So after simplification we are getting this integral that is converted into a complex integral. And here second order, these are the two values of the poles. Out of these two poles only one pole lie within the circle, so we have to find residue of this pole only. So residue of fz at that point is coming as 1 upon 3i and integration over closed curve c fz dz, that is the given integral is equal to 2 pi upon 3. And these are additional problems you can try with. So I want to just tell you that here Cauchy's all theorem, Cauchy's theorem, maybe Cauchy's integral formula as well as Cauchy's residue theorem. These are very easy. So make a lot of practice and try to score out of marks in this topic also. All the best. Thank you.